Hello everyone, welcome back to Sulekha physics classes. It is the most easiest way to learn all the concept of physics through this class. Today I am going to start one short revision of chapter 4, that is moving charges and magnetism. In this chapter I think only one part is related, that is cyclotron, but there are many other important topics like Ampere Circuit Law, Biosavart Law, Lorentz force, moving coil galvanometer, force between two parallel current carrying wires, how galvanometer is converted to ammeter. All these topics are very important. So I will focus more on these topics, but I will discuss other topics also. So let us start quick revision of this chapter, moving charges and magnetism. As the name suggests, what is chapter name? Moving charges and magnetism. How this moving charges is related to magnetism, magnetic properties, right? You know, the region around any charge is what? Electric field. Here, the region around any magnet or any current carrying wire is called magnetic field, right? It was first proved by Oersted. Oersted was the scientist who discovered how this electricity and magnetism are related to each other. So first you must know about first magnetic field. It is denoted by capital B, right? Notation of magnetic field is capital B, and it is a space around a magnet or any current carrying wire where the magnetic influence can be experienced. It means when anything comes near around a magnet or current carrying wire, it experiences magnetic force. Magnetic influence can be experienced. This magnetic field is a vector quantity and its SI unit is Tesla. It is denoted by capital T. In CGS system, its unit is Gauss, denoted by capital G. And what is relation between this SI and CGS system? 1 Tesla is equal to 10 to the power minus 4 Gauss. Right. So how this magnetic field is produced? Who had discovered this one? So Oersted was the scientist who discovered that when, suppose his experiment is like this one, this is a current carrying wire or loop or circuit, and he kept one magnetic needle around this wire. What happens? When current starts flowing through this circuit or wire, the needle starts showing deflection. It means something is there around this current carrying wire which influences the needle, and needle starts deflecting. If the direction of current is reverse, then again needle deflects in the opposite direction. So Oersted observed that magnetic needle deflects when current passes through a wire. It means moving charge or current carrying wire produces something around it, right, which this magnetic needle experiences, and that something is what? Magnetic field. So that's why magnetic field is the region around any magnet or this current carrying wire in which the magnetic influence can be experienced. Thus, Oersted observation was that a moving charge or current carrying wire produces magnetic field in the surrounding region. Suppose this is a current carrying wire. Current is flowing through this wire, and if any charge kept near this one, and this charge is suppose moving in this direction with velocity v. So this charge experiences some force due to this current carrying wire. It means around this current carrying wire, magnetic field is present. So Oersted was the first scientist who observed that a moving charge or current carrying wire produces magnetic field around this wire, right? Around this wire. But there is another observation: if this charge is at rest, so no magnetic influence can be observed. It means magnetic influence is only observed when the charges are in motion. So we studied about in the previous chapter that when charge at rest, it only produces electric field, right? But when charges are in motion, When the charges are in motion, it produces both electric and magnetic field. So magnetic field is only when the charges are in motion, but electric field is in both cases, when the charges are at rest or charges are in motion. So this was about Oersted observation. After this, what is the value of this magnetic field? What is direction of this magnetic field? I will discuss. Take a screenshot of this one fast. Next is Biosavart Law. This law gives the magnitude of magnetic field due to a current carrying conductor. Suppose this is a current carrying wire and I current flows through this wire. Now what is the magnetic field due to this current carrying wire at a particular point? But according to this law, it does not give the magnetic field due to the whole current carrying wire. It gives small magnetic field due to the small current element. Let's suppose DL is small current element, right? And it gives magnetic field, a small magnetic field due to this small current element. What is the magnitude of that magnetic field? So according to it, the small magnetic field at point P, and suppose it is at a distance r from this current element, right? This small magnetic field at a distance r is proportional to I. How much current flows through a wire? It is proportional to dl, current element. It is proportional to sine theta. Theta is the angle between this current element and r, and it is inversely proportional to 1 by r square. Magnetic field varies as distance increases or decreases. So overall, the magnitude of the small magnetic field at a distance r due to this current element dl is given by, it is proportional to I ds sine theta by r square, or dB equal to mu naught by 4 pi I ds sine theta by r square. Here I is a scalar quantity and I want direction of magnetic field. That's why I suppose this current element dl, and it is a vector quantity, and this current element is always in the direction of current. So this current element and r makes angle theta, and magnitude of that small magnetic field is given by mu naught by 4 pi I ds sine theta by r square. What is this mu naught? Mu naught is permeability of free space, and its value is given by 4 pi into 10 to the power minus 7. Must remember this one, Newton meter square Tesla meter per ampere. Now, what is direction of that magnetic field? So you must write first in vector form. How you write in vector form? 1 r multiplied here with sine theta and 1 r here. So it becomes mu naught by 4 pi I ds sine theta, r and r multiplying and dividing r. So it becomes mu naught by 4 pi. You can write I dl. I is a scalar quantity, so no need for this direction. I is a scalar quantity. So this ds sine theta r, you can write ds sine theta r as dl cross r. dl cross r is what? dl r sine theta, and denominator r cube. So in vector form, small magnitude due to the current element at a distance r from the current element is given by mu naught by 4 pi I dl cross r by r cube. Now from here it's clear that what is the direction of this magnetic field? It is along the direction perpendicular to this dl cross r. So first take a screenshot, then I will discuss about its direction, right? Next is direction of magnetic field. You know magnetic field at point P due to a current element is dl at a distance r is given by mu naught by 4 pi I dl cross r by r cube. So direction of this magnetic field is given by this dl cross r vector. It is the direction of dl cross r. So you can write the direction of magnetic field is perpendicular to the plane containing dl cross r. You know na, a vector A cross B, resultant of this vector is C, and direction of C is what? Perpendicular to the plane containing A and B. So in the same way, direction of this magnetic field is in the plane containing dl cross R, right? And it is represented by right hand screw rule. What is this right hand screw rule, right? If you place a right handed screw at a point P perpendicular to this plane and rotate its handle from DL to R, so the direction in which the screw advances gives direction of magnetic field at this point. So here in this case at point P, rotate the handle from DL to R. The screw goes inward. So direction of magnetic field at point P is inward. Here inward or perpendicular to this plane is represented by cross type, right? And here suppose at point Q, so the screw rotates outward. So direction of magnetic field at this point is outward. It is denoted by dot. Outward magnetic field and perpendicular to this board or plane is represented by dot, and inward magnetic field is represented by cross type, right? There is another rule, that is right hand thumb rule. It's very simple and easy. What is direction of magnetic field with the help of this right hand thumb rule? According to this rule, place the thumb of your right hand in the direction of magnetic field and curl your finger to the point at which magnetic field is required. Then curling your finger, the finger goes inward. It means direction of magnetic field at point P is inward. Here you put your thumb in the direction of current and curl your finger to the point at which magnetic field is required. So here at this point the finger curls outward. So direction of magnetic field at point Q is outward. In this way you can determine direction of magnetic field with the help of this right hand thumb rule and screw rule. Cross means inward field and dot means outward field, right? Okay, please take a screenshot. Then we'll move to the next topic, that is applications of this Biosavart law, right? Now, next important topic is magnetic field due to a circular current carrying wire loop. This topic is also very important from examination point of view, right? Magnetic field due to a current element according to Biosavart law. Suppose here this is a current carrying wire and there is a small current element DL and magnetic field at a distance R due to this current element DL is what? dB equal to mu naught by 4 pi I dl sin theta by R square. But here we have to find magnetic field due to a circular current carrying loop, right? So how you find this one? For this, let us consider R is the radius of this current loop and suppose current is flowing in anti-clockwise. Thus let current I is flowing. Okay, so first I consider one current element on the circular loop, and to that current element I have to apply Biosavart law and find a small magnetic field. Then we integrate over the whole loop, right? For this, so let us consider this is a small current element DL. And what is direction of this DL? Okay, wait. Okay, suppose this is a circular current carrying loop and current is flowing in anti-clockwise direction, right? So current is flowing like this one. So I consider the topmost point of this loop. Here current is going in this outward direction, right? So current element DL is also in this direction along tangential to the surface. The direction of current element is this one, and you have to find magnetic field along the axis of this loop. From the center, this one is at point P, you have to find magnetic field, right? So you join this point DL to this point P, let it be smaller, right? Now what is the angle between this DL and R? DL is along this one, tangential to the surface, right? And R is what? From this DL to a point where magnetic field is to be determined here. So this DL and R is at 90 degree. So according to Biosavart law, a small magnetic field at point P due to this current element DL at the top of the loop is what? Mu naught by 4 pi I dl sin theta by R square, and here theta is 90 degree. Angle between DL and R is 90 degree. So it becomes dB equal to mu naught by 4 pi I dl sin 90 is 1 R square, right? This is equation number 1. What is direction of this magnetic field dB? Here dB is both perpendicular to DL and R. So DL is along this one, tangential to the surface, and R is this one. So according to right hand palm rule, direction of magnetic field is what? This is thumb and this is the direction of magnetic field dB, right? This one is the direction of magnetic field dB due to this current element. Okay, now let us suppose another diametrically opposite end here, right? dl, and due to this current element, again magnetic field at this point is along this direction. So let this angle be phi, which makes along the axis of this ring to this r, phi angle. So you know, according to this formula, dB is perpendicular to dl and r. dl is along this one, r is along this one, and dB is along this one. So this dB is perpendicular to this r distance. This one is 90 degree. If this one is phi, so this total is 90 degree. It means this is 90 degree, na? So this is 90 minus phi, and these r and b are perpendicular to each other. If total is 90 degree and this one is 90 minus phi, it means this becomes phi. Now you resolve this dB into two parts, components. One is along, one is perpendicular. So along this one is dB cos phi and this side dB sin phi. In the same way, this dB is also resolved into two components, dB cos phi and dB sin phi. Here distance is same r, so magnitude is same, dB is same. But this dB cos phi, due to this first current element top and bottom, they are opposite to each other, they are cancelled to each other. So by symmetry, dB cos phi equal to 0, only dB sin phi is left. So how you find total magnetic field at point P due to the whole circular current carrying loop? You have to integrate this dB over the whole ring and only sine component is left. You add whole sine component over the whole ring. So this B equal to dB sin phi. Now what is the value of dB? dB is mu naught by 4 pi I dl by r square. Put the value here and sin phi. Now in this figure, what is sin phi? This is a triangle, right angle triangle, right? Hypotenuse is there. This one, sin phi. Sin phi is what? R by small r. Sin phi is r by small r, right? So you put this value here, you get mu naught by 4 pi I r by r cube integration of dl. Why I have taken all these terms outside? Because all these are constant. Mu naught by 4 pi is constant, I is also constant, r is constant, and distance to the point where magnetic field is to be determined is same from all the points on this loop, right? This is same from this circular loop. So r is also constant here. That's why only integration of dl is left. Now what is the integration of dl? First you take a screenshot fast. Okay, now I'm going to rub this side, right? Hope you have noted all these things. Okay. So after this, B is what? Magnetic field B becomes mu naught by 4 pi I r. What is the value of this small r? R is r square plus x square root, right? So this becomes r cube means r square plus x square 1 by 2 or whole cube, right now? And this side integration of dl, right? This becomes mu naught by 4 pi I r by r square plus x square 3 by 2. What is the value of this integration of dl? Integration of dl over the whole ring. It means circumference of this ring is what? 2 pi, radius is capital R. So integration of this dl becomes 2 pi r. You write here integration of dl is 2 pi r, right? So magnetic field due to this current carrying loop is what? This 2 cancel, pi cancel, mu naught I r square by 2 is 2, okay, r square plus x square 3 by 2. This is the magnetic field due to a circular current carrying wire along the axis, right? Along the axis, which is a distance x is B equal to mu naught I r square by twice r square plus x square 3 by 2. Okay, note down this equation. Let it be equation number, I don't know, write it 2. Now special cases of this equation. This is the magnetic field at a distance x from the axis of the ring. Now you have to find magnetic field at the center of the ring. So at the center of the ring, how you find? At the center of the ring, this x distance is what? 0. So special cases, right? First one is magnetic field at the center of the ring, right? So at the center of the ring, what is the value of x? X is 0. Then this B becomes mu naught I r square by twice x is 0 means r square, 2 cancel, only r cube is left here, and once again r square cancel, this becomes mu naught I by 2r. This is the value of magnetic field at the center, right? B equal to mu naught I by 2r. Please note down fast. Okay, may I adopt this one? Okay. Now after this, magnetic field at the center of the ring. This is here at the center of the ring, magnetic field is maximum magnetic field at the center of the ring. Now if the ring has n number of turns, then what is the value of magnetic field? So second is if n number of turns are there, then what is the value of magnetic field at the center of the ring? You just multiply by n. So B equal to mu naught Ni by 2r. This is the magnetic field due to n number of turns at the center of the ring, right? Okay, please note down. And one thing you must remember, in case of this circular loop, it's very easy to find direction of magnetic field if, according to right hand thumb rule. You just point your palm of right hand along the direction of the current, right? Like this one, pointing direction of current. Then the finger represents the direction of magnetic field. Suppose current is flowing in this one, just put your finger along the direction of for all the palm fingers along the direction of the current. Then this direction of magnetic field gives direction of magnetic field at any point, right? So please note down. Okay, then after that we'll move to the next topic. Okay, one more thing, how you plot graph of this magnetic field and distance. Please note down. Wait. Okay. Graph is also important. It may come in 1 marks question. You have to draw graph between. So at the center of the ring, magnetic field is maximum. So you have to draw graph between this magnetic field is along this side and distance is along this side. So at the center of the ring, magnetic field is maximum, right? So here magnetic field, the value of magnetic field is maximum, and on both sides that magnetic field decreases. As the distance increases, magnetic field decreases. B is inversely proportional to this x. So at the center, magnetic field is maximum, and then on both sides magnetic field decreases. So this is the graph between B and x. Just remember this, so right here at x equal to 0, B is maximum, right? And at x equal to infinity, B is minimum, B tends to 0. So like this one, you have to draw graph between B and R. This is also very important, it may come in 1 marks, right? So please take a screenshot of this one, then we will move to the next topic. Now, next important topic is Ampere Circuit Law. It is also an alternative method to find magnetic field due to a current carrying wire, like Biosavart Law. But Biosavart Law is used in simple cases, and with the help of this Ampere Circuit Law, we can determine magnetic field due to complicated circuits, right? Like Coulomb's law, we can determine electric field due to Coulomb's law also, but in complicated case we use Gauss theorem. In the same way, in place of Gauss theorem in electric field, here I am using Ampere Circuit Law in magnetism, right? So according to this law, it states that line integral of magnetic field around any closed coil is equal to mu naught times total current passing through this loop. Okay, suppose this is a current carrying wire, and you know a current carrying wire, magnetic field is around this current carrying wire, right? So this is magnetic field around this one, current carrying wire. Now at any point you find that direction of magnetic field is what? Tangential to the surface at that point. It means current element and B magnetic field is along the same direction. Both are tangential to the surface. And this line integral of this magnetic field over this loop is equal to how much current passing through this loop. So suppose around this loop, how much current is passing? Around this loop, this current I is flowing through this loop, right now. So line integral of magnetic field over this closed loop is equal to mu naught times total current passing through this loop. So mathematically you can write in line integral of B dot dl equal to mu naught times current passing through this closed loop. Like Gauss theorem is what? Line integral of electric field over a closed surface, the E dot dl, here B dot dl. In that one, total charge enclosed within that surface, right now 1 by epsilon naught times total charge, here mu naught times total current in magnetism. So you can write easily in this way, line integral of magnetic field over around any closed loop is equal to mu naught times total current I inside, total current passing through this loop, right? Mathematically you can write, and this law is useful only if B is tangential to the loop. B tangential to the loop means B and DL are always along the same line, tangent to the surface. So that B dot DL is what? B DL cos theta and B DL angle is 0. So cos 0 is 1. So take B outside. B is constant everywhere on this loop. Okay, for simplification. So we have to draw a surface or loop like that one on which magnetic field is constant at every point on that loop, and this closed surface or loop is what? Amperian loop, like in Gauss theorem, Gaussian loop. So to find magnetic field due to any current carrying wire or any circular current carrying wire, any shape, you have to first draw one loop that is called Amperian loop enclosing that current, right? And also it becomes easier if B is normal to the loop. In that case B is 0, and loop should be symmetric about the current. Suppose this is a current carrying wire, so you draw a loop so that loop should be symmetric about this current carrying wire, and B is constant everywhere on that wire. In that case this law is very useful. So I am going to derive using this Ampere Circuit Law magnetic field due to a long straight current carrying wire. How you find using Ampere Circuit Law? Suppose this is an infinite long current carrying wire, I current is flowing, okay, and you have to find magnetic field at point P at a distance r due to this infinite long wire. So how you find magnetic field at point P? First you draw a loop passing through that point P, right? You draw a loop passing through this point P, and this loop should be symmetric about this current so that B is constant everywhere on that loop, right? So you draw one loop, you know, if you take this point current element here, magnetic field is tangential to this surface along this direction. At this point B is this direction, at this point B is along this direction, at B is along this direction at this point. So if you take from the top, suppose this is a wire and this, suppose this is a wire and magnetic field is around this wire, and top view, if you look these things from the top of this one, so you find that there is one circle and current is coming out, right now. So this is the top view. There is one circle and current is coming out through this circle. So I have shown the direction of current outward with the dot inside this circular wire, circular loop. Current is coming out if you look from the top side. So I represent the direction of current by dot. It means current is outward, and at every point B is tangential to this surface, like this one. This point B is this direction, this point B is in this direction, this point this direction. Now apply this by Ampere Circuit Law and find current due to this infinite long wire. Here B is tangential to DL, and due to symmetry, field is also constant at every point on this loop. So you can write B dot DL equal to what? B DL cos 0. B and DL is along the same direction, tangential to the surface. So cos 0 is 1. So B dot DL, B is constant also. So you take B outside, integration of DL. Suppose R is the radius, or at a distance R from the wire at which field is determined. So this circumference of this wire is what? 2 pi r. So integration of DL is 2 pi r. So B dot DL becomes B dot 2 pi r. Now from Ampere Circuit Law, this B dot DL is what? How much current is flowing? I current. So mu naught I inside. From this equations 1 and 2, B dot 2 pi r equal to mu naught I, and from here B equal to mu naught by I by 2 pi r. This is magnetic field due to infinitely long straight current carrying wire using Ampere Circuit Law. What is the value? B equal to mu naught I by 2 pi r. In this way, you find magnetic field by applying Ampere Circuit Law. So to apply this law, you must remember that you draw one loop enclosing that current, and that loop should be symmetric about the current, and B is also tangential to the surface and must be constant on the surface, so that we can easily apply this law. Please take a screenshot. Then we will move to the next topic, that is solenoid and toroid. Now, next important topic is solenoid. We have to apply Ampere Circuit Law to determine magnetic field inside a long solenoid. But what is this solenoid, and what is the need of this solenoid, right? Actually, you know, magnetic field, to increase the magnetic field, you have to increase current, but the value of mu naught is very small. So large amount of current is required to produce strong magnetic field, which is not possible. So there is only one solution. We have to increase number of turns in the coil to produce strong magnetic field, and a large number of insulated copper wire wound closely in the form of helix. This is a large insulated copper wire. It is wound closely in the form of helix, and this forms solenoid. If you pass a current through this solenoid and it's suspended freely, it rests in north-south direction. It means it behaves like a magnet. If you change the polarity of the battery, direction of current reverses, right? So, but how you wound insulated copper wire in the form of helix? You require one base. So this is a non-conducting base over which insulated copper wire is tightly packed to form solenoid. So solenoid is an insulated copper wire wound closely in the form of helix, in the form of concentric circles. Concentric circles means all the coils have same center. Suppose this is R is the radius of each coil and L is the length of solenoid. If the solenoid is very large, it means length is very greater than the radius of the coil, each coil, and that solenoid is called ideal solenoid. In that case, length of the solenoid is very greater than the radius of each coil. So in this way, solenoid is used to produce large strong magnetic field, right? Now, what is the direction of magnetic field around this solenoid? So to determine the direction of magnetic field, you cut this solenoid into two parts. Suppose this is a base and this one is solenoid. Large number of insulated copper wires are wounded over it. You cut this solenoid into two parts. You observe that in one part current is going in upward direction, in another part current is coming in downward direction. Again upward, again downward, again upward, again downward. So you cut the solenoid into two parts. Now this is the two-dimensional figure. In one part, all the coils current is going outward, and outward current is shown by the dotted, right? And in another part, in all the coils current is coming downward, right? Inward field. So inward current is shown by the cross type, right? So, okay, wait. So this is the cross section of two-dimensional figure of the solenoid. If you cut the solenoid into two parts, in the upper part current is going in upward direction. It means outward current. In this one, downward current. Now, what is direction of magnetic field in this part? Here, current is outward. This is, suppose current direction is outward. So you put your right hand thumb rule, according to right hand thumb rule, you put your fingers, curl the fingers around this. Direction of current is upward, you curl your fingers. So this is anti-clockwise. It means direction of magnetic field is what? Anti-clockwise. In all the loops, direction of current magnetic field is anti-clockwise. In this one, lower section, current is in downward direction. If current is downward, you curl your four fingers. It is again in what? Which direction? This is clockwise direction, right now? Current is downward, you curl your fingers in this clockwise direction. So here direction of magnetic field is what? In all the coils, clockwise. Now here you observe that here in this part, direction of magnetic field in all the coils is what? This direction from left to right. Right now, here also in the lower section, direction of magnetic field is what? In all this clockwise, it means from left to right. So inside this solenoid, direction of magnetic field is from left to right, right? But outside the solenoid, what happens? Suppose this is, right? Suppose this is two coils, one coil and two coil. In the first half part, direction of magnetic field is what? Around this magnetic field is there. Here also magnetic field is there. In the upper part, direction of magnetic field is anti-clockwise, right now, and in this lower part, direction of magnetic field is clockwise. So you find that in the upper part, in one coil, magnetic field is downward, another coil, magnetic field is upward. So both cancel each other. Here also, in downward part, in one part, magnetic field is going like this one, another coil, magnetic field is coming in this direction. Both cancel each other. It means the total magnetic field outside this solenoid is 0. Only magnetic field exists inside the solenoid. Due to these two parts, magnetic field is from left to right direction and also exists inside the solenoid only. So here some assumptions are there. Magnetic field lines outside solenoid is 0. Magnetic field lines inside solenoid is straight. These field lines are straight, parallel, equidistant. It means uniform magnetic field, constant magnetic field exists inside the solenoid. And you have to find the value of that magnetic field inside the solenoid using Ampere's Circuit Law. Is it clear? So this is about solenoid. What is solenoid? How you find the direction of magnetic field in case of solenoid. Now you have to find the value of that magnetic field using Ampere's Circuit Law. Please take a screenshot of this one first. Now I am going to find magnetic field inside an ideal solenoid using Ampere's Circuit Law. You know solenoid, this is how you divide the solenoid into two parts. This one is one part, this one is another part, and you also know that there are some assumptions are there that magnetic field outside solenoid is 0, right? Magnetic field lines inside solenoid is straight, parallel, equidistant, that is uniform magnetic field inside the solenoid. Also length of the solenoid, this length of the solenoid is very greater than the radius of the solenoid, and again number of turns in per unit length is very high. It means small n is very high in case of ideal solenoid. Now I am going to derive magnetic field inside this ideal solenoid using Ampere's Circuit Law. Suppose this is the axis of the solenoid. You have to find magnetic field at point P, right? So to find magnetic field at this point P, you draw one Amperian loop passing through this point P. So this ABCD is Amperian loop, right? Amperian loop, and let I be the current in one turn. In one turn, I current is flowing. So according to Ampere's law, what is this line integral of this B dot dl is mu naught I inside. Line integral of A, B, C, D is equal to mu naught I inside. I inside is total current through this loop A, B, C, D. Now along A, B, B dot dl, then BC length, then CD length, then DA length. So total magnet B dot dl is ABCD is AB, BC along CD along DA equal to mu naught I inside. Okay, so please note down this one. Okay, hope you have written. I'm going to rub this side, right? Now, you have to find B dot dl along AB, BC, CD and DA separately. First, B dot dl alongside BC, right? So, along BC, B dl. What is the value of B dot dl along BC? Magnetic field is in this direction and current is flowing in the loop is in this direction. Both are at 90 degree. It means B dl cos theta means cos 90 and it becomes 0. In the same way, along B dot dl along this DA. This is also B dl along DA is cos. Here also magnetic field is along this direction, current is moving in this direction. Both are 90 degree. So cos 90 becomes 0. And also magnetic field along this CD part. Along this CD part, okay, it is a vector. So you put vector sign here, no problem. B dot dl vector. At everywhere you put vector sign, right? Okay. Now along CD, you know magnetic field outside the solenoid is what? 0. So this part is outside the solenoid. So along CD also magnetic field is 0. Now one part is left, magnetic field along AB. So you first write this part becomes 0. Right now BC part becomes 0, this CD part becomes 0 and this DA part becomes 0. So net magnetic field B dot dl only AB side is left and this is equal to mu naught I inside, right? You find that, you know that magnetic field is uniform inside the solenoid, you take B outside B and also you find one thing that, okay, wait, this is AB, B dl cos theta, right now? B is along this direction, left to right, and D current is also along this direction. DL length is also along this direction. So here angle is 0. So this becomes B dl cos 0. Cos 0 is 1. So it just B dl. And you know B magnetic field is uniform inside the solenoid. You take B outside. It's just integral of this dl. Along AB, and let us suppose that the length of this AB is suppose L. Okay, the length of this AB is L. So in place of integral dl you write B dot L. So in this way you find integral of along AB is this B dot L. So this equation becomes equation number which one? Okay, this equation number 1. This becomes, in place of this one B dot dl, you write B dot L equal to mu naught I inside. Now you know that I is current in 1 turn, but inside this Ampere loop there are number of turns are there. So how you find the total current inside this Ampere loop? I inside. First you note down this one fast. Okay, may I rub this side? Okay, I'm going to rub this one. Okay, after this one, your aim is to find I inside. For this, let us suppose that N be total number of turns per unit length. Total number of turns per unit length, right? And let us suppose N be the total number of turns. Total number of turns. It means this small n is number of turns per unit length. So from here total number of turns becomes N into L. This much number of turns is in this Amperian loop ABCD. Now I be the current in one turn. So total current I inside this loop becomes number of turns is NL. In one turn current is I. So in this number of turns current is what? NI. NI means NIL. This is the value of I inside. Now from this equation 2, B dot L becomes mu naught I. In place of I inside you write NIL. Right? This LL cancel, B equal to mu naught NI. This is the value of magnetic field inside a ideal solenoid. Right? So hope you have understood this one. To find the magnetic field inside the solenoid, you just draw one Amperian loop passing through that one. Then apply Ampere Circuit Law, B dot dl equal to mu naught Ni. Then after that, you get only B dot dl along AB. Other BC, CD, DA, B dot dl is 0, right? Now you have to find I inside. I be the total current. I inside total current inside the Amperian loop ABCD, and you know I is in one turn. So you find first number of turns inside this ABCD loop, then total current I inside is NIL, and this way you have to find magnetic field inside a long solenoid. From here it's clear that if number of turns B is proportional to N, so if number of turns is very high, large number of turns are wounded over a non-conducting vase, so we produce strong magnetic field, uniform magnetic field inside a long solenoid, right? Hope you understood. Please take a screenshot of this one. Okay, one thing is left shall I rub this one? Okay. In 1 marks question it may generally come that draw a graph between magnetic field and distance x from the axis of this solenoid. So variation of magnetic field B, right, along the axis of the solenoid with distance x, distance from its center, Suppose this is the axis of the solenoid center, and how magnetic field varies when you move from towards the end of the solenoid. So let us suppose like this one, right? This side magnetic field and this side is distance from the axis of the solenoid. Suppose this is the center of the solenoid. A solenoid is of total length is suppose capital L. So this side L by 2 and this side also L by 2. You know, at the center of the solenoid magnetic field is uniform and constant. It is maximum magnetic field, right? And outside that magnetic field decreases. At the end of the solenoid magnetic field becomes half, this side half. Here is B by 2, and then magnetic field you draw like this one, it's okay. At this end magnetic field decreases. So hope you understood. Now next one is toroid. What is toroid? You know already about solenoid. When a solenoid bent into the form of a closed hollow circular ring. When a solenoid is bent into a hollow circular ring, it forms toroid, and when current passes through it, it produces magnetic field. Suppose these are two ends of the solenoid and solenoid is bent into the form of a circular ring. So let us suppose that this is a circular ring and metallic wires are wounded over this ring. So, and this forms toroid, right? What is difference between toroid and solenoid? It is just a circular shape of this solenoid. But one important thing is that in case of toroid, magnetic field is completely locked since there is no air gap and no leakage, right? So, a strong magnetic field is produced inside the toroid. Now, how you find the magnetic field inside the toroid solution? Toroid, solenoid. You can say toroid also, you can say toroid and solenoid also. So, here you find that in the upper side current is entering and then current is coming down. Again current going up, then current down. So here this is the cross section of this toroidal solenoid. In the upper part, current is going in upward direction, then downward, then upward, then downward, then upward, then downward. So in the lower part, direction of current is inward, shown by the cross type. In upward part, current is shown by the dot type, outward direction, right? Now you have to find magnetic field outside the toroidal solenoid. Inside means this free space, and between these two gaps, upper and lower, there is this is circular, hollow circular ring, na? So there is a gap between these rings. So to find magnetic field in between this, inside this toroidal solenoid, inside this free space, outside the toroidal solenoid. And you find this case also that magnetic field inside this free space is 0, outside is also 0, only magnetic field exists in between the inside this toroidal solenoid. So for this, let us suppose that n is the total number of turns and small n is number of turns per unit length, right? First to find magnetic field inside a toroid that is at point P. It means in open space. So you have to find magnetic field at point P. What you have to do? You have to draw one Amperian loop passing through this point P, right? This one is Amperian loop. And you find that according to Ampere Circuit Law, B dot dl is mu naught I inside. But inside the open space, current is passing through this one, na? Only over this circular ring. Inside the free space toroidal solenoid, no current is there. So I is 0, it means B is 0. So magnetic field inside the toroid, that is in open space, is 0. Okay, please note down. Then next we will find magnetic field outside the solenoid. Fast. Now magnetic field outside point Q, outside this toroid, it means at point Q. So to find magnetic field outside this toroid, you draw an Amperian loop passing through that point and apply Ampere Circuit Law. B dot dl equal to mu naught I inside. Now outside this toroid, what is the value of I inside? In every loop, every turn, in one side current is going in upward direction and other side current is going in downward direction, and I upward equal to I downward. So net current in every loop is what? 0. For each turn I net is 0. So magnetic field outside this toroid is also 0. So we find that magnetic field inside the toroid in free space, open space, it is 0, and outside the toroid also it is 0. Only magnetic field exists inside the solenoid, between these two, right? So you have to find next one, magnetic field inside the toroid at point R. This one is very, very important. And to find magnetic field at point R inside the toroid, it would draw one Amperian loop passing through this point R. And according to Ampere Circuit Law, B dot dl equal to mu naught I inside. Now you know that what is the value of direction of magnetic field on this loop, right? Here only this inward current is there. If current is inward, magnetic field is always tangential to the surface. At every point, magnetic field is tangential to the surface. It means theta is 0. So B dot dl equal to B dl cos 0. It means B cos 0 is 1. Integration of this dl. Let us suppose that length of this whole Amperian loop, radius is smaller. So perimeter length is 2 pi r. Then Ampere Circuit Law becomes B dot 2 pi r equal to mu naught I inside. Now you have to find this I inside at this point R. For this, you have to suppose that let I be the current in one turn. And how many turns, total number of turns? Let N be the total number of turns. So total current inside this total number of turns N is what? Ni. So I inside is Ni. Therefore, B dot 2 pi r equal to mu naught I inside means Ni. From here you get B equal to mu naught Ni by 2 pi r in terms of total number of turns. In terms of number of turns per unit length also you can write. Okay, first you note down this one. In this way you have to find magnetic field inside that toroid is this one. Mu naught Ni by 2 pi r. R is the distance at which magnetic field is to be determined inside the toroid, and N is total number of turns. Please take a screenshot of this one fast. Okay, may I rub this one? Now you have to compare magnetic field between solenoid and toroid, right? You know magnetic field due to solenoid is what? Magnetic field due to solenoid is B equal to mu naught Ni, right? Now you have to write magnetic field due to toroid in terms of number of turns per unit length. So N is number of turns per unit length. Here length of this Amperian loop is what? 2 pi r. So you write N by 2 pi r. Okay. So from here N becomes N into 2 pi r. You put this value in this equation. B equal to mu naught. What is the value of N? N 2 pi r. I by 2 pi r. This 2 pi r to pi r cancel. It becomes mu naught Ni. It means magnetic field due to toroid and magnetic field due to solenoid have equal magnitude. Both are same. So you have to write magnetic field inside solenoid is equal to magnetic field inside toroid. But this magnetic field inside toroid is completely locked because there is no air gap, no leakage is there. This is the advantage, right? There is no loss of magnetic field. So this is about solenoid and toroid. Hope you understood. Please take a screenshot. Then we'll move to the next topic. Now, next important topic according to your syllabus is force on a moving charge in a magnetic field. First, you know what is magnetic field. If any current carrying wire is there, around this wire, the region around this wire is nothing but magnetic field. And you know what is the direction of that magnetic field. According to right hand thumb rule, you place your thumb in the direction of current and curl your four fingers. The direction in which the finger curls gives direction of magnetic field. Here you put your thumb in this current direction, curl your fingers. Your fingers going inward, right? So direction of field is what? Inward this side. But this side, curl your fingers is in outward. So this side magnetic field has outward direction. Outward means outward to this plane of this board or plane of paper. And this is represented by dot, and inward field is represented by cross. Inward field means perpendicular to the plane of paper or plane of this board, and it is inward. And this dot shows it is perpendicular to this plane and the field direction of field is outward, right? So this is magnetic field. Now you know current carrying wire has some magnetic field around that wire, right? Now if any other charge enters in this region, then what happens? If that charge is at rest, then there is no effect, right? If charges are at rest, then no effect. No, it does not experience any force. But if that charge is in motion, suppose this Q charge enters in this magnetic field with velocity V. Now when it enters in this magnetic field, it experiences some force, and that force is called magnetic force, and due to that force it changes their path and deflects in this direction. So a moving charge experiences a force in a magnetic field, that is called magnetic field, and this force only exists when the charge is in motion. When the charge is at rest, no magnetic effect, no magnetic force. So the expression for magnetic force is Q V cross B. Q is the charge, right? V is the velocity of that charge, and B is the magnetic field in which it enters, and it is always given by Fm equal to, Fm is magnetic force, Q V cross B. It means the direction of this magnetic force is what? It is perpendicular to the plane containing V and B. Suppose this is plane. In one direction charge is moving, magnetic field is in another direction, then the force is perpendicular to this plane. containing V and B, either inward or outward, right? And in magnitude, Fm is given by QVB sine theta, where theta is the angle between V and B, right? So I think magnetic force is clear. It only exists when the charge is in motion. If charge is at rest, it means V is 0, and if V is 0, it means force is also 0. In another case also force is 0 if theta is 0 or 180 degree. Here if you put theta 0, then sine 0 is what? 0, or sine 180 is also 0. In both case, magnetic force is 0 or minimum. Sine 0 means V and B both are in the same direction, right? And 180 means if B is in this direction, then V is in opposite direction. In both the cases, magnetic force is 0. It means the particle does not experiences any force if angle is 0. Another case, if V is 0, then force is also 0. If theta is 90 degree, if angle between V and B, if in one direction V is there, in another direction B is there, and theta is the angle between V and B. If angle is 90 degree, in that case, sine 90 is what? 1. So in that case, force is QVB, maximum force, right? And one thing you remember, when force is 0, it means there is no effect on charge. So the particle, motion of the particle is a straight line. If maximum force it experiences, then path is circular. I will prove this one after this, right? So just remember this thing, expression for magnetic force and which condition it is 0 or maximum. After this, what is the direction of this magnetic force? There are two rules. One is right hand screw rule and the one is right hand thumb rule, right? So please take a screenshot first, this one first. Now direction of magnetic force. How you give the direction of magnetic force? You know the expression for magnetic force is what? Fm equal to Q V cross B. So this direction of magnetic force from this expression, it's clear that it is perpendicular to the plane containing V and B. So first rule for this is given by screw rule. What is a screw rule? Place a screw at this point and rotate the screw from V to B. Suppose rotate the screw from this V to B. So rotation is what? Anti-clockwise. And if the rotation is anti-clockwise, then what is direction for magnetic force? Outward, right? If the rotation is clockwise, suppose V is this side and B is this side, right? Then rotation is clockwise. If the rotation is clockwise, then what happens? Clockwise rotation, direction of magnetic force is downward or inward, like this one. Okay, so this is a screw rule. And if the charge is negative, the direction of force is reverses. Here direction of force is upward now, but if this charge is negative, then direction of force is downward. So a negative charge, the direction of force is reversed. This is screw rule. Another important rule is right hand thumb rule. Curl fingers of this right hand from V to B. V is here, B is here. Curl these fingers from V to B. Then the direction of this thumb gives direction of magnetic force. It means if curl your fingers from V to B, direction of this thumb is upward, it means direction of force is upward or outward. So curl fingers of right hand from V to B, then the direct thumb gives direction of magnetic field, magnetic force, sorry. Okay, so direction of magnetic force is given by these two rules. One is screw rule and the one is right hand thumb rule. It's very simple. Just curl your fingers of this right hand from V to B, the direction in which the thumb points gives direction of magnetic force. So please take a screenshot. After this, we'll discuss Lorentz force. Now, next one is Lorentz force. What is this Lorentz force? Suppose any charge, moving charge, enters in a region where both electric and magnetic field is present. Then that charge experiences electric force as well as magnetic force. And this sum of this electric and magnetic force is called Lorentz force, total force, right? So Lorentz force is, you know, electric force is what? QE magnetic force is what? QV cross B. So total force is both sum of electric and magnetic force. It means this F equal to QE plus QV cross B. It means QE plus V cross B. This is the expression for Lorentz force, right? Sum of total electric and magnetic force. After this, what is the expression for magnetic force on a current carrying conductor? If any current carrying conductor of length L is placed in a magnetic field, then it experiences some force. What is the value of that force? F equal to IBL sine theta, or you can write in vector form F equal to IL cross B. This is the expression for force on a current carrying conductor of length L. Theta is the angle between L and B. Here L is, theta is the angle between this B and L. L is the length of the conductor, or direction of current is also along the length of the conductor. As current is a scalar quantity, so for direction we use here L or length vector, right? And the direction of this L cross B gives direction of force, right? Suppose L is in this direction, right? Now L is, and B is in this direction. So curl your right hand finger from this L to B, then direction of thumb gives direction of magnetic force, right? This is direction of, or you can give the direction with the help of a screw rule also. So this is the expression for magnetic force on a current carrying conductor. You must remember this one, F equal to IBL sin theta or IL cross B. If theta is 0, if both L and B, if this conductor is placed in the direction of magnetic field, then total magnetic force is 0. Then it does not experience any magnetic force. If theta is 90 degree, it means if B is in one direction and L is in another direction. If the angle between B and L is 90 degree, then it experiences magnetic maximum force, right? So you must remember these things. After this, we'll move to the next topic, that is motion of a charged particle in a magnetic field. Please take a screenshot fast. Now, motion of a charged particle in a magnetic field. It means when a charged particle enters in a magnetic field, what is the motion of that charged particle? Motion means in which direction it moves. What is the path taken by that charged particle? You can say trajectory of the charged particle. So you know that magnetic force is given by QV cross B, or you can write QVB sin theta, where theta is the angle between V and B. To find the motion of a charged particle in a magnetic field, there are some assumptions. First is magnetic field is uniform. It means magnetic field is constant, right? Second is magnetic field is perpendicular to this plane of paper or plane of this board, or inward type. Here I assume that the direction of magnetic field is perpendicular to this plane or this board and in inward direction. So inward type magnetic field is denoted by this cross. Cross means field is perpendicular to this board and inward direction, right? Now, if a charged particle enters in this magnetic field in the direction of magnetic field, it means V and B are in the same direction. In that case, theta is 0 and magnetic force is also 0. It means there is no effect on the charged particle. So, this angle theta equal to 0 provides linear motion. In the direction in which the particle is moving, it moves in the same direction. There is no change in direction of the particle, right? But when theta is 90 degree, it means when, suppose here field is inward and particle moves in any in this plane. Suppose in this direction particle is entering, we're moving with velocity v. So v is in this direction and field is inward and perpendicular to this plane. So when this particle enters in this field, the angle between this perpendicular to this plane is this one, right? And particle is moving in this direction. So angle between this velocity v and this magnetic field is what? 90 degree, right now? So when theta is 90 degree, Fm is maximum, magnetic force is QVB, because sine 90 is 1. And the particle experiences some magnetic force, and this magnetic force acts as a centripetal force and it provides circular motion of the particle. Suppose here field is inward, right? So, and particle is moving in this direction. So, curl your fingers from V to B. Force is acting in this direction. This is direction of force, right? Upward. And so, the particle in place of moving like this one, it takes round due to this force. Again at this point, the motion of the particle is tangent to this. Particle is moving in this direction. V is in this direction. But magnetic field is inward. So, velocity is in this direction. Magnetic field is inward. It means force is in this direction. This is direction of force. In the same way, at this point, V is in this direction and magnetic field is inward. So, thumb point gives direction of force. It means force is in this direction. Again, at this point, velocity is what? Downward, in this side, downward, and magnetic field is inward. So, curl your fingers from this V to B. Force is in this direction. This is direction of force. So, this, when particle enters with angle theta, right, then this provides circular motion of the particle. And this circular motion means centripetal force. Here, magnetic force acts as centripetal force and it provides circular motion of the particle. So, two things you have learned, that when theta is 0, it means both particle enters in the direction of magnetic field. There is no change in direction of charged particle. It moves as it is. It provides linear motion. When theta is 90 degree, it means when suppose particle is in this direction, B is in this direction. So, it provides force either inward or outward force, right? Perpendicular to this V and B, and it provides circular motion. So, these two things clear. But what happens when a particle enters in this magnetic field with some angle theta, not along and not perpendicular, with some angle theta? It means suppose particle is entering with velocity V. So, it has two components. One is along B and another one is perpendicular to V. One is V parallel, another one is V perpendicular. V parallel means suppose angle between this V and B is theta. Suppose B is in this direction, right? V is this direction. Particle enters in this direction with some angle theta with B. So, it has two components. One is V parallel along this one and V perpendicular along this one. V parallel means V cos theta. V perpendicular means V sin theta. And you know, V parallel provides what? Linear motion. It is along B. And V perpendicular means V sin theta provides circular motion. So, when particle enters at some angle theta with B, then there are two independent motion. One is linear and the one is circular. And when these two independent motions combine, circular plus linear, it gives helical path. Particle is moving in a circular motion and also it covers some linear distance. It means it moves, the particle follow helical path or spiral path, right? If the particle moves in a helical path, there is some radius of this helical path. There is a pitch distance between these two circular motion. There is a linear distance that is called pitch. So, in this way, when particle moves at some angle theta with the magnetic field, it has both linear and circular motion, and both motion combine to give helical path of the particle. Now, next topic is what is the radius of this helical path, what is the pitch, frequency, time period of rotation, right? So, please take a screenshot first. Okay, now you know when a particle enters in a magnetic field at some angle theta, then it has two independent motion. One is linear and the one is circular, and both motion combined gives helical or spiral path of the charged particle. Now you have to calculate the radius of this helical path, time period, frequency, pitch, everything. So first one is radius of helix. Here you know that magnetic force here acts as a centripetal force to provide circular motion. So here magnetic force is equal to centripetal force. What is the value of magnetic force? Q VB sin theta, and centripetal force is mv square by r, where r is the radius of this circular motion, here helix, right? Now this circular motion is at angle 90 degree, so here theta is 90 degree, you put 90, sin 90 is 1, so Q VB equal to mv square by r, and from here you get r equal to mv by QB, 1 VB cancel. It provides, this expression gives radius of this helical path. It's very important when solving numerical, right? Here you easily find that this V is directly proportional to radius. As the velocity increases, radius of the helical path also increases. Next one is frequency of rotation. You know, there is a relation between linear velocity and angular velocity. This V is linear velocity, omega is angular velocity, and V equal to R omega. From here omega is V by R. You put the value of R from this equation. V by, in place of R you write mv by QB, right? This V cancel, it becomes omega equal to QB by M. And you know angular frequency is related with this one, angular velocity, omega equal to 2 pi nu. So here nu becomes omega by 2 pi. This nu is angular frequency. Omega is what? QB by M. You put the value here, QB by M divided by 2 pi. So this angular frequency becomes QB by 2 pi M, right? In this way you calculate angular frequency. Then time period of oscillation. Time period of oscillation means time taken by a particle to complete one rotation, from suppose here to here. So how much time taken by a particle to complete one oscillation is called time period of oscillation, and it is given by t equal to just simply time period is what? Reciprocal of angular frequency. So 1 by nu, you get frequency is what? QB by 2 pi M. Reciprocal of this one is 2 pi M by QB, right? You can find this time period also in this way. Time period is what? 2 pi by omega, because omega is 2 pi by t na, so t is 2 pi by omega. You simply put the value of omega from here, QB by M. So 2 pi, here QB by M. From this it becomes 2 pi M by QB. So you can find this way also and that way also. Time period of oscillation is t equal to 2 pi M by QB. Now last one is pitch. Pitch is the linear distance moved along the direction of magnetic field, right? So distance moved along magnetic field means this linear path, linear distance, this is called pitch, and this pitch is provided by this direction, this side in the direction of magnetic field. Which component of V? V parallel, it means V cos theta. So pitch is equal to V parallel into T. V parallel is V cos theta, T is 2 pi M by QB. So you get pitch equal to 2 pi mv cos theta by QB. In this way you find radius, frequency, time period and pitch of the helical motion, right? Please take a screenshot. After this we'll move to the next topic. Now next important topic is force between two parallel current carrying conductors. It was first observed by Ampere that two parallel straight conductors carrying current in the same direction, it means parallel current, then the force between the two conductors is attractive in nature. If the current is flowing in opposite direction in the two parallel conductors, it means anti-parallel current, then the force between them is repulsive in nature, right? So how? Let it be more clear with the help of this diagram. Suppose first parallel currents, these two are infinitely long straight conductors 1 and 2. In conductor 1 current I1 is flowing, in conductor 2 current I2 is flowing. You know a straight current carrying wire produces magnetic field around it. So what is the magnetic field produced by this conductor 1 carrying current I1? This side on wire 2, on conductor 2, current is flowing in this direction, upward na? So put your thumb of right hand in that direction of current and curl your fingers. So direction of magnetic field is what? Inward, this side. So here inward field is represented by cross type and this is due to wire 1. So I write here B1, right? Again, due to this current in conductor 2. Current is flowing in upward direction, I2 current. What is the value of magnetic field here on wire 1, conductor 1? Current is flowing in upward. You curl your fingers, it moves outward. It means here magnetic field due to this current, second conductive wire is outward, B2. It is shown by the dotted line. Okay. Now, what is the force experienced by this second conductor having current I1 due to this first wire? Due to first wire, magnetic field here is B1, and on the second wire, current is flowing in upward direction. So, what is direction of force? According to right hand thumb rule, if current is flowing in upward direction, magnetic field is inward, it means force is in this direction. So this one F2 is the force experienced by this second wire, right? Now what is the force experienced by the first wire due to this magnetic field of second wire? Here current is in upward direction and magnetic field is outward. So how you find a direction of force? According to right hand thumb rule, conductor is in, current is flowing in upward direction, but magnetic field is outward. So you curl your finger from upward to outward, force is in this direction. So force experienced by first conductor F1 is in this direction. Now you find here that these two forces have equal magnitude. It will be clear with the help of this how equal magnitude, but these two forces are opposite in direction. It means if the current flowing in the same direction, the force between the two conductors are attractive in nature, right? Is it clear? Now, if current is flowing in opposite direction, it means anti-parallel current is flowing. So, how this force is repulsive in nature? So, okay, suppose here current I1 is flowing in first conductor, and due to this I1 current, magnetic field on this second conductor is inward, B1, right? Okay. Now here on the second wire, current is flowing in downward direction. Okay. Current is flowing in downward direction. So what is the magnetic field here on wire 1? Current is flowing in downward direction. You curl your finger. Your finger goes in inward. So here again, due to this current I2, current is flowing in downward direction, magnetic field on wire 1 is inward, B2, right? So you find magnetic field due to first and second wire. Now what is the force experienced, in which direction force experienced by second wire? In second wire, current I2 is flowing and field is in inward direction. So what is direction of force? Current is upward, field is in which direction? Sorry, current is downward here, na? Wait. Here current is downward, I2. Current is in downward direction and magnetic field is inward. It means current is downward from right hand thumb rule. Current is in downward direction and magnetic field is inward. This thumb gives direction of force. It means force is here, this side, outward. Now on first wire, magnetic field is again inward and current is also upward. So current is upward, magnetic field is inward. It means force is this side. So these two forces are again equal and opposite, but these two move away from each other. These two forces are towards each other. These two forces away from each other. It means the force between the two conductors are repulsive in nature. Is it clear? I think if a current is flowing in the same direction, then the force between the two conductors is attractive in nature. If the current is flowing in opposite direction between two parallel conductors, then force between the two conductors is repulsive in nature, right? Now what is the value of that force? Force magnitude is same, only if direction of current is reverse, then force also changes their nature, right? So let us find the magnitude of this force. This figure, suppose this is figure 1 and this one is figure 2. In figure 1, okay, magnetic field due to this current I1 on wire I2 is what? B1. Magnetic field due to current I1 at any point on wire I2 is given by, what is the formula for current carrying wire magnitude, magnetic field? Mu naught I1 2 pi r. R is distance between these two infinite conductors, right? So magnetic field produced by conductor 1 having current I1 is given by mu naught I1 2 pi r. This is the value of B1, right? Now, what is the force experienced by this second wire due to this magnetic field B1? So, force on wire 2 current I2 is given by what? What is the formula for force? I2 BL sin theta. Here current is I2 and magnetic field is B1, L sin theta. Here L and here magnetic field is inward and conductor is placed like this one. So, angle between L and B is what? 90 degrees. Sin 90 is 1. So, you just write I2 B1 L. Here theta is 90 degree. Now, you put the value of B1 here from this equation, mu naught I1 by 2 pi r. You get the value of F2 as mu naught I1 I2 L by 2 pi r, right? Similarly, this is the force experienced by second wire having current I2, right? Now, what is the force experienced by this first wire? So, here magnetic field is due to second wire. So, magnetic field due to current I2 on wire I1 is B2 and B2 is given by due to I2 the mu naught I2 by 2 pi r. Now, what is the force on wire 1 having current I1? This is given by I2 B2 L. Here B2 is there, current is I1 and again the angle between current and magnetic field is 90 degrees. So, sin 90 is 1. So, you just write F1 equal to I1 B2 L. You put the value of B2 from this equation, mu naught I2 by 2 pi r. You get the value of F1 as mu naught I1 I2 L by 2 pi r. From these two equations 2 and 3, it's clear that these two forces, force experienced by second wire and force experienced by first wire having same magnitude, but from this figure they are in opposite direction. So, from the figure F1 is equal to F2 and it follows Newton's third law of motion. I think it's clear to you how these forces are attractive in nature and how these forces are repulsive in nature with the help of this diagram and what is the magnitude of this force. Both have same magnitude, both wires experiences the same force but only direction is opposite. If current is in same direction, they are moving forces towards each other, it means attractive force. If current is flowing in opposite direction, so both force moves away from each other. So these are repulsive in nature, right? It was first observed by Ampere. So 1 ampere, definition of 1 ampere is given by from this definition, right? What is the magnitude of force? Force is mu naught I1 I2 L by 2 pi r. If from here you write force per unit length, F by L is what? Mu naught I1 I2 by 2 pi r. Here if both wires have current 1 ampere, if I1 I2 is 1 ampere and distance between the two conductors R is also 1 meter, then what happens? F by L becomes mu naught this one by 2 pi into R is also 1. So you put the value of mu naught 4 pi into 10 to the power minus 7 by 2 pi. This 2 2's are pi cancel, it becomes 2 into 10 to the power minus 7 Newton per meter. This is force per unit length. So from here we can define 1 ampere. 1 ampere is the current which when flow in each of the two infinitely long wire kept 1 meter distance apart. Okay? 1 ampere is the current which when flow in these two infinitely long current carrying wires separated by distance 1 meter produces a force of 2 into 10 to the power minus 7 Newton per meter between them. It produces force how much? 2 into 10 to the power minus 7 Newton per meter between them. This is the definition of 1 ampere and it's also very, very important, right? Sometimes it may ask. So this is about the force between two parallel current carrying conductors. Hope you understood. Please take a screenshot of this one. Now, next important topic is torque experienced by a current loop in uniform magnetic field. Current loop means you can say magnetic dipole also. Magnetic dipole. This current loop behaves like a magnetic dipole having magnetic moment I into OA, right? So when this current loop is placed in a uniform magnetic field, it experiences some torque, and this torque is the basis of working of all galvanometer electric motor. So this topic is very, very important. Let us discuss it. Suppose these are north and south pole of the magnets, and you know direction of magnetic field is from north to south pole. So this is the direction of magnetic field from north to south. Now you place one coil in the plane of this magnetic field. A, B, C, D is a rectangular coil carrying current I. I current is flowing in this coil. Now we discuss two cases. Case 1, when plane of loop is along magnetic field. It means what? Suppose this is rectangular loop A, B, C, D, and magnetic field is along this direction. So plane of loop and magnetic field both are in the same direction, right? Now what happens when this current carrying rectangular coil is placed in this magnetic field? It experiences some force, right, in all the sides of this rectangle. So the force experienced by this side BC, magnetic field is in this direction, and this BC current is also in this direction. Both are in the same direction. It means angle is 0. So net force here is 0. FBC is 0, and also magnetic field is in this direction and current is in this direction. The force on AD arm is also 0. Now what is the force experienced by this AB arm? This is rectangular coil A, B, C, D, and magnetic field is in this direction. So angle between this magnetic field and this current in AB arm is at 90 degree. So force experienced on this arm AB is BIL sin theta. Theta is here 90 degree. Angle between magnetic field and length element AB is what? 90 degrees. So this force on AB is BIL. In place of L, let us consider that this side is B, and this side is A. A and B are the length and breadth of this rectangle. So force on arm AB is what? BIB, right? B is this side, length of this AB. Now what is direction of this force according to Fleming's left hand rule, right? Magnetic field is in this direction. This forefinger represents direction of magnetic field, right? And current is in which direction? This side, right? Now, sorry, upward. So current is in upward direction. This is left hand rule. Magnetic field is in this direction. Current is upward. So this thumb represents direction of magnetic force. It means force is in downward direction. Force on arm AB is in downward direction, right? Again, force experienced by this arm CD. Here again magnetic field is this direction, but current is now in which direction? Downward direction. Magnetic field is in this direction, current is in this direction. So force experienced by this arm is upward. This one is the force experienced by arm CD in upward direction, right? So what is the value of that force? BIL sin theta. Again this theta is 90 degree here, so BIB, and direction of force is upward. These two forces are equal and opposite. So net force is what? 0. Magnitude of these two forces are same, but direction is one is upward and the one is downward. So net force is 0. But is there any torque? Because line of action is not same. This is rectangular coil, right? On this side force is in upward direction and this side force is in downward direction, but this line of action is not same. This is different point, this one is different point. So it experiences some torque. Torque means rotational motion. This rectangular coil experiences some torque because the two forces are equal, but their line of action are not same. And you know, if you look this figure from the top of this one, so you just find that there is this line, single line. This is top view, right? Top view. This side is there, one side force is upward and the side force is downward. So this force upward is force on arm CD, FCD, and force downward is FAB, and this is the angle this distance between the two forces is what? This one is the line of action, right? So this distance is A. A is the length and B is the breadth of this rectangular coil, right? So torque is force into perpendicular distance between those forces. These two forces are equal. You write here F into perpendicular distance is A. So F into A. What is the value of F? Force BIB. BIB into A. And this B into A is what? A is this length, B is breadth. So A into B is area of the loop. You can write here A. A is the area of the loop. So torque experienced by this rectangular coil is IBA, right? This is the case when the plane of this loop is along direction of magnetic field. Both are in the same direction, right? So in this way you can determine torque. And what is the direction of this torque? This is the one force is upward and the force is downward. It starts rotating in this direction along the axis of rotation. This one is the axis of rotation and direction of torque is downward, perpendicular to this plane, right? Or you can say in the direction of dipole moment. So this is the expression of torque. Now second case, little bit different is there, when plane of loop makes some angle with the direction of magnetic field. First, this is direction of magnetic field and this is the rectangular coil. Both are in the same plane. Now you rotate this loop with some angle theta. This is direction of magnetic field. It means this magnetic field and area vector of this one makes some angle theta, right? So what happens? Let us discuss. First take a screenshot of this one. Now case 2, when plane of loop makes angle theta with the direction of magnetic field. What happens when the plane of loop makes angle theta? First time, case 1, magnetic field is this direction and plane of loop is also in this direction. Now you rotate this coil so that now this time magnetic field is still in this direction, right now, but it makes angle theta with this loop, right? So figure is like this one. Magnetic field is still in this direction and but it makes angle theta with the area vector. Area vector you can say magnetic dipole moment, because magnetic dipole moment is I into A. So whatever direction of area vector is direction of magnetic dipole moment. Now this time there is some angle between magnetic dipole moment and magnetic field. Again force along AB. Force on AB is in which direction? Magnetic field is this direction, current is upward, so again force is in downward direction, and on this arm again CD arm force is in upward direction, right? So I've written here force on arm AB is again BIL sin theta. Here again theta is 90 degree, right? Angle between this magnetic field and this length element current I. So at this side of this length is what? B, and here is A. So BIB, force on AB. Again force on arm CD is BIB. These two forces are equal opposite, net force is again 0, but here again the line of action is different. This time line of action is not this one. This time line of action, this also rotates, right? So here is the top view when you when magnetic field is in this direction but you rotate this plane. So from the top view it is like one straight line, this one, right? This is A, this one is A, and force on arm this CD side is upward and force on arm AB is downward. These two forces are again equal opposite but line of action is different, so it experiences some torque, and that torque is given a force into perpendicular distance between them. Now what is the perpendicular distance between them? This is one force and this is another force. Perpendicular distance between them is this one, right? Now how you find this one? This total is A, it means this one is A by 2 and this one is again A by 2, and this is the area vector. Area vector is perpendicular to this plane, right now, area. So when this rotates, area vector also rotates. So this is area vector and this one is magnetic field. Angle between them is theta, or area vector you can say magnetic dipole moment. Both are in the same direction. If this angle is theta, so this magnet area vector and this length, it is at 90 degree, right now. So this one is 90 minus theta, so this angle becomes theta. You just find this angle is theta. So what is the value of this OB, right? Sine theta. From this triangle, sine theta is what? Sine theta is, sine angle is perpendicular by hypotenuse. Perpendicular here is this one, OB. This is perpendicular and by hypotenuse. Hypotenuse is a by 2. So from here perpendicular is a by 2 sine theta. This perpendicular is nothing but OB. OB. So here OB is a by 2 sine theta. Again this one is also a by 2 sine theta. So when you add these two, this becomes a sine theta. And this is the perpendicular distance between these two forces, a sine theta. So in this case tau becomes force into a sine theta. You put the value of force BIB, so it becomes B into A is again area, so IBA sine theta. Only slightly difference, if it makes some angle theta, then there is a sine theta term, so torque becomes IAB sine theta, right? Now again, you know magnetic dipole moment is I into A, so you put in place of I into A what? Magnetic dipole moment MB sine theta, and you can write in this way also M cross B. This is the torque experienced by a rectangular coil when it is placed in a uniform magnetic field, and if it is an n number of turns, then tau becomes NIAB sine theta or tau MB sine theta. You can write in any way. So from this it's clear that this is direction of magnetic dipole moment, this one is field. So what is direction of torque? Torque is in this direction, M cross B. When you rotate M cross B, torque is in this downward direction. So this magnetic field try to orient this current carrying coil. It experiences some torque, right? And so this is the final expression for torque, M cross B, or you can say MB sine theta. Theta is the angle between this M and B, or you can say area vector and magnetic field. Now there are two cases when both M and B are in the same direction. That case tau is 0, and if both are perpendicular to each other, then in that case tau is maximum. This is about when plane of loop makes angle theta with the magnetic field. So this question is very important from examination point of view, right? So please take a screenshot of this one. Now last and most important topic of this chapter is moving coil galvanometer and its conversion to ammeter and voltmeter. The first you must know about this moving coil galvanometer, then how it is converted into ammeter and voltmeter. What is this galvanometer? It is a device which measures or detects small currents in the circuit. It is used to measure whether the current is flowing in the circuit or not. It measures very small amount of current. On which principle it is based? It is based on the principle when current carrying coil is placed in a uniform magnetic field, then it experiences some torque, and that torque is given by tau equal to NIAB sine theta, where theta is the angle between this area vector and magnetic field, and area vector and magnetic field are always perpendicular to each other. It means the coil is placed in a plane of along the magnetic. The plane of the coil is along the magnetic field, so that area vector and magnetic field makes angle 90 degree. So here theta is 90 degree, so torque is given by NIAB, where N is the total number of turns in the coil, I is current flowing through the coil, A is the area of the coil, B is magnetic field, right? What is the construction of this moving coil galvanometer? Actually it consists of a large n turns of insulated copper wire winded over soft iron cylindrical core. Why this soft iron cylindrical core is used? It is strong ferromagnetic material, so that all magnetic field lines passes through this coil and it produces a strong magnetic field. Here this cylindrical magnet is used to produce radial magnetic field, right? So this one end of this coil is connected to one terminal and the end is connected to another terminal, so that when the two terminals are connected, current flows through this coil. Now one end of this cylindrical iron core is connected to a fine wire to a pointer, and pointer is attached to this scale, and another end is connected to a spring. Now what happens when these two terminals are connected? Current starts flowing through this coil and it experiences some torque because this current carrying coil is placed in a magnetic field. This is the top view of this moving coil galvanometer. When you look at from the top of this arrangement, you find this circular, top of this circular, this is a circular coil, and over which a large number of coils are binded, right? So these are large number of turns over this. So this is the top view, and this one is north pole and south pole, right? Magnetic field is in this direction. This is cylindrical magnetic pole, so to produce radial magnetic field, and hence strong magnetic fields, and here soft iron core is used so that all magnetic field lines passes through this coil and it produces strong magnetic field, and a spring is connected to one end of this coil and pointer is connected to one end. Now what happens when it develops some torque now, and this coil starts rotating. When this coil rotates, the spring and this pointer, here is fine wire, both starts twisting and generates restoring torque. That restoring torque is directly proportional to deflection, which this pointer shows. Greater the twisting, greater is the deflection shown by this pointer on this scale, right? So this restoring torque is proportional to phi. It is equal to C phi, where C is a constant called torsional constant. Now as the coil rotates, this is applied torque. What is this? This one is applied torque, and due to this applied torque, spring starts twisting and develops restoring torque. So this is equation number 1, and this one is equation number 2. Now in equilibrium condition, both this restoring torque and applied torque equal, and from this we can determine what is the value, what is the reading shown by this pointer. It means deflection. So please note down this one fast. Okay, may I rub this one, right? This theory is very important. This question every time it comes in the exams, right? So in equilibrium condition, what happens? Wait, black marker. In equilibrium, what happens? This restoring torque is equal to applied torque. Applied torque means when current passes through this coil, it develops some torque. So what is this restoring torque? C phi equal to applied torque is NIAB. From here phi equal to NIAB by C, or you can write NAB by C I. It means this phi is directly proportional to I because all these are constant. C is constant called torsional constant, it is also constant. N is number of turns is also constant. A is area of the coil, and B is magnetic field. So greater the amount of current passes through this coil, greater is the deflection shown by this pointer. It is noted with the help of this scale reading, right? So this is the construction, working and everything theory of this moving coil galvanometer. Please note down this one, it's very important, right? Deflection is directly proportional to current flowing through the coil. So in this way we can measure by note down the reading of this. What the reading shown by this pointer from this scale, we can determine the current flowing through the coil. But with the help of this moving coil galvanometer, we can only measure a small amount of current. We cannot measure large amount of current. For that one, we must convert this galvanometer into ammeter to measure current and into voltmeter to measure potential difference, right? So please take a screenshot of this one fast. Next is sensitivity of galvanometer. What does it mean? What do you mean by sensitivity? Sensitive means galvanometer shows large deflection when a small voltage or current passes through it. when a small voltage or current passes through it, it shows large deflection, right? It is of two types. One is current sensitivity, another one is voltage sensitivity. Current sensitivity means galvanometer shows large deflection when a small amount of current flows through it. So current sensitivity is given by phi by I. And you know what is the value of phi? In the moving coil, we discuss N A B I by C. You put the value here phi, then you get here I cancel, N A B by C. This is current sensitivity. If current increases, deflection also increases, and you can say more sensitive is the galvanometer. And this reciprocal of this current sensitivity is called merit of figure of merit of galvanometer. This is one experiment in class 12, defined figure of merit of galvanometer using this moving coil galvanometer, right? So you have to find these values, and reciprocal of this current sensitivity is figure of merit of galvanometer. Second is voltage sensitivity. When a small unit potential difference is applied, then it shows large deflection in the galvanometer. This is voltage sensitivity. It is equal to phi by V. You put the value of what is V? V is equal to IR, and phi by I you know, current sensitivity, NAB by C, you put here NAB by C, and this is R, where R is resistance of galvanometer coil. This is voltage sensitivity. Now on which factors this sensitivity depends? It depends on number of turns of the coil. It is directly proportional to number of turns, directly proportional to magnetic field, directly proportional to area of coil, current, inversely proportional to torsional constant. So in this way you have to define this sensitivity of galvanometer. It may come in 1 or 2 marks question. It is also important from examination point of view. Now last topic is conversion of galvanometer into ammeter and voltmeter. First into ammeter. You know na, with the help of galvanometer only we can measure a small amount of current and voltage. But if in the circuit large amount of current flows, large amount of potential difference is there, and how you measure? For that one we can convert this galvanometer into ammeter and voltmeter. Ammeter is a device to measure large amount of current in the circuit. Now how you convert this galvanometer into ammeter? For this we connect a small shunt resistance in parallel with the galvanometer, so that whatever amount of current flowing through the galvanometer, only small amount of current flows through this galvanometer, rest amount of current flows through this shunt resistor, and then this arrangement gives ammeter, right? And this ammeter must have a small resistance, so that whatever amount of current flows through the circuit, we can get the same desired amount of current through other side also, right? So this ammeter must have a small resistance, and to produce to construct ammeter we convert galvanometer in parallel with the shunt resistance, right? So both are in parallel connection, so potential difference across galvanometer is equal to potential difference across this shunt resistance. It means Ig, G equal to I minus Ig into S. From here we can find S. S is equal to Ig into G by I minus Ig. So to which range you want to construct ammeter, according to that one we can decide this value of S. And this ammeter is always connected in series with the circuit. You must remember these things, right? This is about conversion of galvanometer into ammeter. Last one is conversion of galvanometer into voltmeter. To convert this galvanometer into voltmeter, we connect a high resistance R in series with this galvanometer, so that when current passes through this galvanometer, it also passes through this high resistance, and it only measures a small amount of potential difference. Rest potential difference is across this high resistance R, so that we can convert this galvanometer into voltmeter by connecting this high resistance in series with the galvanometer. This gives you voltmeter, right? And total resistance of this circuit is what? According to this is in series, so R plus G. By applying Ohm's law, current Ig is equal to V by R plus G, and from here you can get the value of R equal to V by Ig minus G. So according to which range you want to construct voltmeter, you can decide the value of R, right? And this voltmeter is always connected in parallel with the circuit. You must remember this thing. To convert galvanometer into ammeter, we connect a shunt resistance in parallel with the galvanometer. To construct a galvanometer into voltmeter, we connect a high resistance series with the galvanometer, right? And also this ammeter is connected in series with the circuit, and this voltmeter is connected in parallel with the circuit. Please take a screenshot of this one. So with this, I am going to end the class. Hope you like this one shot revision of chapter 4. Actually, this one shot is very big because chapter is also very lengthy. But I have covered each and every topic of this chapter. If you want this type of one shot revision for other chapters, please write in the comment box so that I will make one shot revision for other chapters also. Till then, students, please keep revising and stay tuned with this channel. Thank you.